You've been told that if you hit the speed of light, your time just stops, like someone slams a cosmic pause button on your life. But what does that actually mean for you sitting inside a ship, watching your own clock tick, watching everyone else's race ahead? In this video, we're going to walk right up to that edge, where seconds stretch, years twist, and light itself lives in a strange place where before and after blur together. If you've ever wondered whether you could outrun time or what really happens as you push closer and closer to that ultimate speed limit, stay here, because once you see what time stops at light speed really implies, your normal idea of time won't survive the next few hours. But before we continue, please subscribe to the channel to give your support. Let's continue. First, lock in the number we're talking about. In a vacuum, light travels at about 299,792,458 meters per second. We usually round that to 300,000 kilometers per second, and if you like miles, that's around 670 million miles per hour. This is not a rough estimate. It's one of the best measured constants in all of science. Every beam of light in empty space, every radio wave, every X-ray hits that same speed, no matter who is observing. Now, stack normal speeds against that. A typical passenger jet does around 900 kilometers per hour, about 560 miles per hour. Compared to light, that is roughly 0.8 of light speed, basically zero on the relativistic scale. One of the fastest human-made spacecraft, like Voyager 1, tears through space at about 17 kilometers per second, roughly 38,000 miles per hour, which feels huge compared to airplanes. But even that is only around 6/10,000ths of light speed. Not one of our rockets, probes, or space stations has ever reached even 1% of light speed. We are orders of magnitude below the regime where relativistic effects really explode. So when someone says to you, at light speed, time stops, they're talking about a limit we have never actually reached with any object that has mass. That should make you ask a hard question. What exactly do we mean by time stops? And what is this time that is supposed to stop? In physics, time is not a mood. It's not this class feels long or that movie went by fast. Time is defined by what a clock measures. A clock is any system that repeats some regular process you can count. Your heartbeat is a crude clock. A swinging pendulum is better. But the real reference now is an atomic clock. Take a cesium atom, it naturally vibrates at a very precise rate. We literally define 1 second as a specific number of those vibrations. So when physicists say time slows down or time is dilated, they mean a real physical clock based on something like atomic vibrations accumulates fewer ticks compared to some reference clock. Picture two identical, very precise atomic clocks. One stays on Earth with you, one goes on a high-speed journey in a spacecraft. When they are brought back together and compared, if one clock has counted fewer seconds than the other, that means less time passed along that clock's path through the universe. There's no psychology involved, no feeling of time. There are just fewer counted ticks. So if you push this idea to the extreme and talk about time stopping at light speed, you are really saying that, in some limit, the time measured along that path shrinks towards 0 ticks, 0 accumulated duration. Now, how did we even get the idea that motion changes the rate of time? Before Einstein, the default view, the Newtonian view, was that time flows the same everywhere, like a universal background, and velocities just add up in a simple way. If a car moves at 50 kilometers per hour, about 31 miles per hour, and someone runs on the roof of that car at 10 kilometers per hour, about 6 miles per hour, then a person standing by the road says that runner is going 60 kilometers per hour. You just add the speeds. There's nothing in Newton's equations that says, stop here, this speed is too high. 1 million kilometers per second is just as legal as 10 kilometers per second. There is no built-in speed limit at all. So if that's the picture, how do you even notice something is wrong? How do you test whether there really is a special speed in the universe that refuses to behave like any other speed? That takes us to the late 1800s and the Michelson-Morley Experiment. At the time, people thought light was a wave moving through some invisible medium, an ether, the way sound waves move through air. The Earth moves around the Sun at about 30 kilometers per second, around 19 miles per second. If light is moving through an ether and the Earth is moving through that ether, then sometimes you should be moving into the wind and sometimes with the wind. That should make the measured speed of light slightly different in different directions, just like flying a plane into a headwind or with a tailwind changes your ground speed. Michelson and Morley set up an interferometer, basically a precise optical device with light beams sent along two perpendicular paths, each maybe a few tens of meters long, then recombined. If the Earth is moving through an ether, the light going with the motion and across the motion should take slightly different times to travel those paths. When you rotate the device, that difference should change, and you should see a shift in the interference pattern, bright and dark bands moving. They were trying to detect a tiny change in light's travel time, corresponding to just a few kilometers per second difference out of roughly 300,000 kilometers per second. That's like trying to detect about a 1 centimeter difference in a building that's 100 meters tall, or a tiny fraction of an inch in a 300-foot skyscraper. They saw nothing. No matter how they oriented the apparatus, no matter when they measured, the speed of light came out the same within their experimental accuracy. Over time, more experiments improved the precision, but the results stayed the same. There was no detectable change. Light speed looked invariant, independent of the Earth's motion. That's a direct clash with the simple just add velocities rule from Newton's world. So now you're stuck with a sharp question. If experiments keep telling you that the speed of light in vacuum is always the same for everybody, how do you fix your theory? Do you bend light's behavior, or do you bend your ideas about space and time? Einstein's radical move in 1905 was to treat the experimental facts as non-negotiable. He said, let's assume two things. First, the basic laws of physics look the same to all observers who are moving at constant speed in straight lines. We call them inertial observers. Second, the speed of light in vacuum is a fixed constant for all of those observers, about 300,000 kilometers per second, about 186,000 miles per second, regardless of how fast the observer is moving. If you accept both of those statements, then you are forced to give up Newton's absolute time. Why? Because if everyone, no matter how they're moving, must measure the same light speed, you cannot let them all agree on what counts as 1 second and 1 meter in the old way. The conversions between what one observer measures and what another observer measures can't just be add this speed and shift this position. The simple old velocity addition rule breaks. Instead, you need a new set of rules that tie space and time together in a more complicated way, so that whenever someone measures light speed, they always get the same number. Those new rules are what we call the Lorentz Transformations. You don't need the explicit formulas here, but you should know what they do. They tell you if observer A measures some position and time for an event, and observer B is moving at some constant speed relative to A, what position and time B will assign to that same event. In the Newtonian limit, when speeds are tiny compared to light, these rules almost exactly match the old simple ones. But as speeds grow, they start to differ. They mix space and time together. A time interval that one observer sees can partly look like a space separation to another, and vice versa. Built into those transformations is the guarantee that every inertial observer, no matter their relative speed, measures the same light speed. And tucked inside them is the effect we call time dilation, moving clocks ticking slower, and length contraction, moving rods coming out shorter along the direction of motion. At this point, you might think, okay, this sounds like ugly bookkeeping, just a complicated conversion chart between different people's measurements. Is there a cleaner way to picture what's going on, so it doesn't feel like a bunch of arbitrary corrections slapped onto Newton? That's where Hermann Minkowski comes in, a few years after Einstein. He looked at these new transformation rules and realized they all become much simpler if you stop thinking of space and time as two separate things. Instead, you treat them as different directions in a single four-dimensional structure called spacetime. You already know three spatial dimensions: left, right, forward, back, up, down. Minkowski adds time as a fourth coordinate, multiplied by the speed of light to put it in the same units as space in the math. Then, any event in the universe, like you snap your fingers here, now, gets four coordinates, one time coordinate and three space coordinates. In this space-time picture, you can define a kind of distance between events, not just in space, but in space-time. It's not the usual Pythagoras rule from school, because time enters with a different sign in the formula, but the idea is similar. You combine how far apart two events are in space and how far apart they are in time into a single quantity called the space-time interval. This interval is the same for all inertial observers, even if they disagree about the separate space and time pieces. When you move from one observer to another using the Lorentz Transformations, the coordinates change, but this space-time interval stays fixed. This is where light gets a special role. The paths in space-time that light follows, between emission and absorption, are exactly the ones where this space-time interval is zero. We call those light-like or null paths. For objects with mass, like you, any physical path through space-time between two events has a positive space-time interval. We call those time-like paths. For speeds that would require faster than light travel, the interval would come out as a different type. We call those space-like, and those aren't allowed for real particles. So why does this matter for the claim that time stops at light speed? Because proper time, the time your own clock measures along your path, is directly tied to that space-time interval. For time-like paths, the ones you can actually travel, the interval is positive, and your clock accumulates a positive amount of time between events. For light-like paths, the interval is exactly zero, which means the proper time along that path is zero. In other words, in this geometric language, light really does travel between two events without any proper time passing along its trajectory. That is the rigorous version of the statement that time doesn't pass for light. The tension now ramps up because this space-time geometry is not optional. It's built into the way we've seen nature behave in every precise test. If light owns those zero interval paths and your world line must always stay in the region with positive interval, the natural question is, how close can you get? As your speed climbs toward light speed, how does your own proper time respond, and how does that look from the outside? To answer that, you need a simple concrete machine you can analyze that clocks use light itself as the ticking mechanism, so you can literally watch time stretch as speed increases. How do you actually see time slow down? Not as a slogan, but inside a simple machine you can picture in front of you. Start with the most stripped-down clock you can build in your head. Two mirrors facing each other, 1 meter apart, about 3 feet. A single particle of light, a photon, bounces between them, up, down, up, down. Every time it hits a mirror and comes back, you call that one tick of the clock. In the frame where this clock is just sitting still on a lab bench, the photon travels 1 meter up and 1 meter down, so 2 meters in total every tick. Light moves at about 300 million meters per second, or about 186,000 miles per second, so you can work out how long a tick takes. 2 meters divided by 300 million meters per second is roughly 6.7 nanoseconds. That's 6.7 billionths of a second. That gap between one bounce and the next is the proper time for this little clock. That's how much time the clock itself experiences per tick when it's at rest. So far, this is just a fancy stopwatch, nothing dramatic. The question is, what happens to this ticking when you throw the whole setup across the room at a good fraction of light speed? Now picture the exact same clock, same mirrors 1 meter apart, same photon, but this time the whole device is moving sideways at left to right at 80% of light speed. That's about 0.8 times 300 million meters per second, roughly 240 million meters per second, roughly 540 million miles per hour. From the point of view of someone watching from the lab, the photon no longer goes straight up and straight down between the mirrors. While it moves upward, the mirrors themselves are sliding sideways at huge speed, so the photon's path becomes diagonal, like drawing a zigzag line instead of a straight vertical line. Here's the key point. The photon still has to move at light speed. The universe does not let it speed up or slow down in a vacuum just because the mirrors are moving. So if the photon now has to travel a longer diagonal path between bounces, but it cannot change its speed, that means it must take longer in lap time to complete each bounce cycle. Longer path at the same speed means more time between ticks. To the person riding with the clock stuck between the mirrors, nothing looks different. The photon still goes straight up and down in their own frame. They still see that 6.7 nanoseconds per tick. But to the outside observer, watching the whole device blast by, each tick of that moving light clock takes more than 6.7 nanoseconds. That mismatch is time dilation, right there, in a device that uses light as the timing mechanism. So, how big is that effect? And how does it depend on speed? Can we put a number on how much the moving clock slows down? Relativity wraps all of this into a single factor people call gamma. Gamma tells you how much slower a moving clock runs compared to a clock at rest in the frame you care about. The rule is the time between ticks that an outside observer sees equals gamma times the proper time between ticks on the clock itself. Gamma depends only on how fast the clock is moving as a fraction of light speed. You take the speed, divide it by light speed, square that fraction, subtract that number from 1, take the square root, and then take 1 divided by that square root. That final number is gamma. Do the numbers for 0.8 times light speed. The speed divided by light speed is 0.8. Square that, you get 0.64. 1 minus 0.64 is 0.36. The square root of 0.36 is 0.6. 1 divided by 0.6 is about 1.67. So at 80% light speed, gamma is about 1.67. That means, as seen from the lab, your moving light clock ticks about 1.67 times slower than the identical clock sitting still. Those 6.7 nanoseconds per tick in the clock's own rest frame turn into around 11.2 nanoseconds between ticks from the lab's perspective. Nothing changed inside the clock. The photon still just bounces, but the way space-time lines up between frames forces that stretch. That's a noticeable slowdown, but it's not yet in the crazy time almost stops regime people love to talk about. So what happens when you crank the speed up even closer to light? Does the slow motion of that clock ramp up gently, or does it start to blow up? Take 99% of light speed next. That's 0.99 times 300 million meters per second, which is about 297 million meters per second, or roughly 662 million miles per hour. Do the same gamma calculation. The speed divided by light speed is 0.99. Square that, you get 0.9801. 1 minus 0.9801 is 0.0199. The square root of that is about 0.141. 1 divided by 0.141 is about 7.1. So at 99% light speed, gamma is about 7.1. That means in the outside frame, 1 second that passes on your moving light clock stretches out to a little more than 7 seconds on the lab's clocks. Or flip it, while 7 seconds tick by on Earth, your light clock only counts 1 second for you. Think about what that means in practical terms. If you had a ship cruising at 99% of light speed relative to Earth, and your onboard clocks, including your body and brain, tick normally from your point of view for 1 minute, outside observers would say about 7 minutes have gone by. For every year you live on that ship, people in the external frame age about 7 years. This isn't a trick of perception. It's built into how time intervals transform between frames. And you can already see how, as you move closer to light speed, the gap between your time and their time widens fast. But the core question for this series is more extreme. If you keep pushing the speed up higher and higher, always staying just below light speed, what happens to gamma? And what happens to the ticking of that light clock as seen from the outside? Does it ever truly freeze? Look at the structure of the gamma calculation again. In words, you take 1, you subtract the square of your speed divided by light speed, you take the square root, then you flip it by taking 1 over that. As your speed gets closer to light speed, the ratio of your speed to light speed gets closer to 1. Its square gets closer to 1 as well. That means the number you are subtracting from 1 gets closer and closer to 0. The square root of a number that is shrinking toward 0 also shrinks toward 0. Then when you take 1 divided by a number that is sliding toward 0, the result blows up. It gets larger and larger without bound. That's what gamma does. At 0.8 times light speed, gamma is about 1.67. At 0.99, it's about 7.1. At 0.999, it's over 20. Push even closer and it just keeps growing. Translate that back to the light clock. The proper time between ticks for the clock itself, its own experience, stays the same. That's 6.7 nanoseconds per bounce in our 1 meter setup. But the time an outside observer assigns between ticks is that proper time multiplied by gamma. As gamma grows, the outside time between ticks stretches more and more. In the limit where your speed approaches light speed, gamma goes to infinity in the mathematical sense. So in that limit, the time between ticks in the external frame becomes arbitrarily large. 1 tick of your clock would correspond to any amount of time you want, a year, a million years, a billion years, depending on how insanely close to light speed you get. This is the mathematical backbone of the phrase, time stops at light speed. It doesn't mean your own clock stops ticking for you. Your proper time never actually freezes as long as you have mass and move below light speed. It means that from the point of view of some external frame, the separation between your ticks stretches so much that to match 1 of your seconds, their clocks would have to run for an infinite amount of time if you ever actually hit light speed. The gap between your time and their time would become infinite. The obvious next question is this just a neat thought experiment with mirrors, or does the real universe ever get close enough to light speed that we can see the slowing of internal clocks in hard data, with particles that actually decay and die on specific timescales? How do you know time dilation is real, and not just some clever story with mirrors and diagrams? Where does the universe actually prove that moving clocks slow down? Start with something very concrete. Unstable particles. Take the muon. It's basically a heavier cousin of the electron. When a muon is at rest in its own frame, its average lifetime before it decays is about 2.2 microseconds. That's 2.2 millionths of a second. If you take the speed of light, about 300 million meters per second, and multiply by 2.2 microseconds, you get a distance of about 660 meters. In more familiar terms, that's around 0.66 kilometers, roughly 2,165 feet, less than half a mile. So if a muon could sit there, then suddenly start moving at light speed and live for its usual time, you'd expect it to cover only that distance before it decays. That already tells you something. Muons are not long-lived. On human scales, they're gone almost instantly. So if you ever see muons hanging around over distances of kilometers or surviving for thousands of a second instead of millions of a second, you know something is stretching their internal decay clock compared to what they would experience at rest. So where do we push muons that hard? Where do we actually slam them close enough to light speed to see this difference clearly? Particle accelerators are the answer. Places like CERN in Europe and other labs around the world use powerful electromagnetic fields to accelerate particles to speeds so close to light speed that for many purposes you can treat them as almost C. For example, protons in the Large Hadron Collider reach something like 0.999999991 times light speed. That's 0.99999999991 multiplied by 300 million meters per second. The missing fraction from full light speed is so tiny that their speed differs from light by just a few meters per second, while the total speed is hundreds of millions of meters per second. Muons in dedicated storage rings or beams in other accelerators reach similarly extreme speeds. At those velocities, that gamma factor we talked about earlier is no longer a small correction. It can reach hundreds or thousands. Remember what that means in plain language. Gamma tells you by what factor moving clocks slow down relative to the lab. For a muon, the clock is its own decay process. If the muon rest frame lifetime is 2.2 microseconds and gamma is, say, 1000, then in the lab, its average lifetime becomes about 2.2 milliseconds. That's 1,000 times longer than you would expect if you ignored relativity. Instead of being able to cover only about 660 meters at light speed, it effectively has the lab time opportunity to cover hundreds of kilometers before decaying, even though its own proper time is still just those 2.2 microseconds. You might say, fine, that's the claim, but does anyone actually count these things, or is this just a theory number? The answer is they absolutely count them. In experiments, beams of muons are stored in circular rings or sent down straight beam lines. Detectors around the ring or at the end of the line record when muons decay by catching the particles they decay into. If there were no time dilation, the number of muons in the beam would drop off very quickly, with a characteristic timescale of 2.2 microseconds in the lab. Instead, what they see is that the muon population decays much more slowly, stretched out by exactly the gamma factor predicted from their measured speed. This isn't a philosophical argument, it's statistics. You plot the number of muons versus lab time, you get a curve that falls off. You fit that curve. The characteristic lifetime you extract is not 2.2 microseconds, it's 2.2 microseconds multiplied by gamma. And gamma itself you can estimate independently from how you accelerated the particles, from their energy and momentum. Those two ways of getting gamma agree. The decay clock inside the muons is running slow relative to the lab frame, exactly the way the light clock thought experiment said it should. Now here's an important subtlety that connects directly to the idea of a hard light speed limit. At these extreme energies, you might think that if you keep dumping more and more energy into a particle, its speed relative to the lab should keep climbing linearly. But that's not what happens close to light speed. Once you are at, say, 99% of light speed, increasing the energy a lot only nudges the speed a tiny bit closer to light speed. The main thing that increases is gamma, and with it, the time dilation and the effective mass, energy. You can see this with a simple comparison. At 99% of light speed, that speed fraction is 0.99, and gamma is about 7.1, like we worked out earlier. Push to 99.9%, 0.999 times light speed, you haven't added much in actual meters per second, but gamma jumps to about 22. Go even closer, 99.99%, and gamma jumps again to around 70. The speed approaches light speed, but never reaches it. What really grows is gamma, and gamma controls how much the particle's clock is slowed relative to the lab. So it's not just more energy means more speed. In the relativistic regime, more and more of that extra energy goes into stretching gamma rather than significantly increasing the velocity. That's why particle physicists talk about ultra-relativistic particles, where their speed is basically stuck extremely close to light speed, and changes in energy mostly change how time-dilated they are and how much momentum they carry, not how many extra kilometers per second they gain. Now tie this back to the time stops at light speed idea. For a muon or any unstable particle, its proper lifetime is fixed. It expects to live 2.2 microseconds in its own frame on average. In the lab, you see a lifetime that is that proper lifetime multiplied by gamma. If you could crank the accelerator so hard that the muon speed really reached light speed itself, gamma would not just be large, it would diverge to infinity. That would mean, in the lab frame, the muon would never decay. Its internal processes would be completely frozen from the lab's point of view. It would be an endlessly stable particle in that external time, while still having only a finite proper lifetime in a mathematical sense. That is exactly the time stops at light speed limit for internal clocks. Of course, the whole point is that we never actually get there. No matter how big the accelerator, no matter how powerful the magnets, you always get just below light speed for any massive particle. Gamma can be huge, thousands, even more, but it's always finite. So you can make the muon's lab lifetime as long as you want in principle by cranking up its speed, but you can never truly freeze it because you can never actually give it light speed. The wall at light speed shows up here as you can make time dilation arbitrarily strong, but you can't make it infinite for a massive particle. So you've got light clocks in thought experiments and muon clocks in accelerators, both telling the same story. Time for moving systems really does slow down relative to the lab, and the closer you get to light speed, the stronger that slowdown becomes. But this is still lab equipment. The next question is, does nature do this on its own above your head, without any human-built machinery at all? How do you test relativity when you don't have a particle accelerator? How do you know that time dilation is happening in the actual sky above you right now? Look up and think about this. High-energy particles from space, cosmic rays, are constantly hitting the top of Earth's atmosphere. Many of them slam into atoms around 15 kilometers up, roughly 50,000 feet. Those collisions create showers of secondary particles, and one of the main products is the muon, the same unstable particle we talked about before, the heavy cousin of the electron. A muon at rest has an average lifetime of about 2.2 microseconds, 2.2 millionths of a second, before it decays. If you take the speed of light, about 300 million meters per second, and multiply it by that lifetime, you get a maximum distance of about 660 meters, around 0.66 kilometers, roughly 2,165 feet. So even if a muon were instantly accelerated to almost light speed and then lived for its standard proper time, it would only be able to cover a few hundred meters before decaying. But remember, most of them are being created around 15 kilometers up. On simple, non-relativistic grounds, they should die long before they ever reach the ground. Here's the problem. That prediction is just wrong. When physicists put particle detectors at sea level, at the surface, they see muons all the time. We're not talking about a rare event. They measure many muons per second for every square meter of detector area. If you build a detector the size of a door, you get a stream of muons passing through it every second. That means a significant fraction of the muons created high in the atmosphere, 15 kilometers up, are actually surviving all the way down to you. That's a direct contradiction with the 660-meter maximum argument, unless something is messing with how their lifetimes show up in our frame. So you're forced to ask, what is extending these muons' lifetimes from our point of view? What is letting them live too long in the lab frame compared to their own internal clock? Relativity gives a very precise answer. Those muons are not crawling downward. They are moving at enormous speeds, very close to light speed. Typical cosmic ray muons have speeds of around 0.998 times light speed or even higher. That's 0.998 times 300 million meters per second, so about 299.4 million meters per second. Still about 186,000 miles per second to within a small fraction. At those speeds, the gamma factor is not small. For 0.998 times light speed, gamma is around 15 or so. That means from the Earth's frame, their internal decay clock is running about 15 times slower than it would at rest. Multiply their proper lifetime, 2.2 microseconds, by gamma, 15, and you get 33 microseconds in the lab frame. In those 33 millionths of a second, moving at 0.998 times light speed, a muon can travel about 10 kilometers or more in the lab frame. Push the speed even closer to light speed, and gamma gets bigger, maybe 20, 30 or more, and the lab frame distance they can cover before decaying becomes easily comparable to or larger than the 15 kilometers of atmosphere between their creation points and the ground. Time dilation stretches their lifetimes in our frame just enough to let a large number of them survive the trip. So the data line up very cleanly. Without relativity, you calculate a maximum travel distance of a few hundred meters, so basically no muon should reach sea level. With relativity and time dilation, you calculate lab lifetimes of tens of microseconds, travel distances of many kilometers, and suddenly it makes sense that we detect them. You put detectors at different altitudes on a mountain, and you actually see the muon flux change in a way that matches the relativistic prediction. That's not a thought experiment, that's measurement. Here's where it gets even interesting. You can describe this situation from two different perspectives and both have to agree on the physics. From the Earth's point of view, the story is simple. The muon has a fixed proper lifetime of 2.2 microseconds. Because it's moving at 0.998 times light speed, its internal decay clock runs slow by a factor of about 15. So instead of dying after 2.2 microseconds of lab time, it dies after roughly 33 microseconds of lab time, which lets it travel far enough to reach the ground. Their clocks run slow, they live longer, is the Earth frame story. From the muon's point of view, you flip the script. In the muon's own rest frame, its proper lifetime is still 2.2 microseconds. It does not feel any special stretching of its own time. Its proper time is what it always is. But what it sees as the thickness of the atmosphere is not 15 kilometers. Because of length contraction, distances along the direction of motion are shorter in the muon frame. The atmosphere is rushing towards it at 0.998 times light speed, and its thickness is squashed by roughly the same factor gamma. So instead of 15 kilometers, the muon sees only about 1 kilometer or even less of atmosphere to cross before reaching the surface. That's a distance it can cover easily in 2.2 microseconds at close to light speed. 2 descriptions, 2 stories, 1 set of consistent events. This symmetry is the whole point of relativity. No observer's description is more true. They just slice spacetime differently. In one frame, moving clocks slow down. In the other frame, moving distances contract. Both are direct consequences of the same space-time geometry we talked about earlier, and both give you the same measurable results. The muon gets from the upper atmosphere to the ground before it decays. There's no paradox, just a different split of space-time into space and time for each observer. Now, think about how this connects back to the light speed limit. When we look at these muons, we never see them cheat. We never see a muon simply go faster than light to beat the clock without time dilation. Their proper lifetime, 2.2 microseconds, never changes. What changes is the way that lifetime is mapped into our coordinate time because of their huge speed. As their speed gets closer and closer to light speed, gamma increases and the lab frame lifetime can be stretched as much as you like. In principle, by choosing a speed close enough to light speed, you can make them survive for milliseconds, seconds, or longer in the lab frame, even though their proper time remains the same tiny value. Push that logic in your head to the limit. If you could somehow accelerate a muon so that its speed reached light speed exactly, gamma would shoot to infinity. And from the Earth frame, its decay would never happen. Its internal processes would be completely frozen in our time. That is the same time stops at light speed limit we've been circling around. But just like in the accelerator case, nature never lets you get there for any particle with mass. The muons always stay just below light speed. Their gammas always very large but finite, and they always eventually decay. So now you have 2 very different arenas. Man-made accelerators and natural cosmic rays, both giving you the same conclusion. As you push something with mass closer to light speed, its internal time slows more and more in the external frame. You can stretch it a lot. You can never turn it into true frozen time. Light speed keeps showing up as a boundary, not a reachable cruising speed. The next question is, does this weird behavior only live in high-energy physics, or is it already affecting the technology in your hand every time you use your phone to find where you are? How do you know this isn't just extreme physics for colliders and cosmic rays? How do you know relativity is quietly running inside something as ordinary as your phone? Right now, if you open a map app and get your location, your phone is talking to a network of GPS satellites orbiting Earth. Each of those satellites is a flying clock. They orbit at an altitude of about 20,200 kilometers, roughly 12,500 miles above Earth's surface, and they move at about 3.9 kilometers per second, around 8,700 miles per hour. On board, they carry ultra-precise atomic clocks, the same kind of technology we use to define the second. The entire GPS system only works if all these clocks, in space and on the ground, stay in tight agreement. Now bring relativity into this picture. From the point of view of someone on Earth, each satellite is moving fast. Not fast compared to light, but fast compared to cars and planes. Special relativity says if a clock is moving relative to you, it ticks slower than your own clock. If you run the numbers for a speed of 3.9 kilometers per second, you find that the satellite's clock should run slower than a clock on Earth's surface by about 7 microseconds per day. A microsecond is a millionth of a second, so that's 7 millionths of a second of lost time per day due to motion alone. If that were the only effect, GPS satellite clocks would lag behind Earth clocks, but that's only half of the story. General relativity says that gravity also affects the rate at which clocks tick. Clocks deeper in a gravitational field, closer to a massive object, tick slower. Clocks higher up, where gravity is weaker, tick faster. A GPS satellite is about 20,200 kilometers up, in a weaker part of Earth's gravitational field than you are at the surface. When you calculate the gravitational effect on time, you find that their clocks should tick faster than ground clocks by about 45 microseconds per day. Now combine those two. Motion slows the satellite clocks by about 7 microseconds per day. Weaker gravity speeds them up by 45 microseconds per day. The net effect is that a GPS satellite's clock runs about 38 microseconds faster than an identical clock on Earth's surface. So if you did nothing to correct for that, every day the satellite's time would drift ahead of Earth's time by those 38 millionths of a second. You might think, 38 microseconds? Who cares? That sounds tiny. But remember, GPS works by timing how long signals, which are radio waves traveling at light speed, go from the satellite to your phone. Light travels about 300 meters in 1 microsecond, roughly 1,000 feet in 1 second. So a 38 microsecond error corresponds to more than 11 kilometers, about 10 miles of distance error. Not all of that error appears instantly because a system uses multiple satellites and constant corrections, but if engineers ignored relativity, your position would drift by on the order of 10 kilometers, around 6 miles per day. After a short time, the system would become completely useless for navigation. This is why the GPS system does not just hope relativity is small. The satellite's atomic clocks are deliberately adjusted on the ground before launch. Their ticking rate is offset so that once they are in orbit, moving at 3.9 kilometers per second, and sitting higher in Earth's gravitational field than you are at the surface, the combination of special and general relativity makes them match Earth's proper time as seen from the ground control frame. On top of that, the system constantly monitors and corrects for smaller residual effects. In other words, the people who design GPS treat relativity as everyday engineering, not as a theoretical luxury. So when your phone locks onto several satellites and triangulates your position, the signals that reach you already know about time dilation and gravitational time shift. Your location fix depends on light speed signals and relativistic time behavior at a speed that is only about 1/10,000th of light speed. That orbital speed, 3.9 kilometers per second, is just 0.0013 times light speed. And even there, the relativistic corrections are measured in tens of microseconds per day, with kilometer-scale consequences if you ignore them. Now, step back and connect this to the question of time stopping at light speed. At a tiny fraction of light speed, 0.0013, the effect on time is small but not zero. You need microsecond level corrections over a day to keep a navigation system accurate. At 0.1 times light speed, 10% of light speed, the effect is much bigger. At 0.5 times light speed, half of light speed, it grows again. At 0.99 times light speed, you saw a gamma factor of about 7, where 1 second on a moving clock becomes about 7 seconds in the outside world. Push to 0.999, 0.9999, and gamma grows into the tens, hundreds, and beyond. GPS is like a low-speed preview. It shows you that even tiny fractions of light speed already force you to take the relationship between motion, gravity, and time seriously, or your technology fails. When you extrapolate from 3.9 kilometers per second up to 0.99 times light speed, 0.9999, you're not changing the rules. You're just pushing the same rules into an extreme regime. The small correction that gives a few tens of microseconds per day in GPS turns into a huge correction that can stretch 1 second on your clock into minutes, hours, or longer in someone else's frame. Now tie this back directly to time. The gamma factor that multiplies momentum and energy is exactly the same gamma factor that multiplies time intervals between frames. It's not a coincidence. In the space-time picture, energy, momentum, and time are all part of the same geometric structure. When gamma gets bigger, you are not just paying more in energy, you're also stretching the mapping between your proper time and the outside world's time. Moving clocks, including your own biological clock, slow down by that same factor gamma relative to an external frame. So as you pump more and more energy into your ship and drive gamma up, your physical resistance to further acceleration climbs, and your proper time, compared to the external universe, slows. One number, gamma, controls both the cost in energy and the distortion in time. So what does time stops at light speed look like when you use those ideas precisely? Imagine pushing gamma toward infinity. As gamma grows, your kinetic energy grows roughly like gamma times mass times light speed squared. In the limit where gamma goes to infinity, that kinetic energy also goes to infinity. There is no way around that. The amount of fuel or power you would need to reach that gamma becomes infinite. At the same time, the time dilation seen from the outside, the factor by which your clock runs slow, also goes to infinity. To match one of your seconds, an external observer's clock would have to run for longer and longer without limit. In the true gamma equals infinity limit, your proper time between two external events shrinks to zero, and the energy cost explodes without bound. That is the sharp physical meaning of time stops at light speed. It's the point in the equations where the price you pay in energy and momentum becomes infinite, and the flow of your own time, compared to an external frame, would be stretched to an infinite mismatch. Nature blocks you from ever reaching that state if you have mass, not by a rule written on a sign, but by making the bill you'd have to pay diverge. So now you have the picture from the massive side. As you drive a massive object toward light speed, energy, momentum, and time dilation all run away together, controlled by the same factor. But there's another side to the story, the side of particles that have no rest mass at all. If massive objects can only approach light speed and never get there, what is life like for something that is stuck at light speed from the beginning? Here's the really strange part. For light, the whole idea of time passing along its path basically disappears. Start with the basic fact. Photons, particles of light, are massless. In a vacuum, they do not have the option to speed up or slow down. They always move at light speed. Not just almost light speed, exactly light speed. About 300 million meters per second, about 186,000 miles per second. That's not just how we usually see them, that's built into the rules of how massless particles work. Now think about what you normally do with any other object. If a rocket flies past you, you can switch to the rocket's point of view. Mathematically, you perform a change of reference frame where the rocket is at rest and the universe is moving past it. That's how relativity works. Different observers slide between frames, each one treating themselves as at rest. For a photon, you simply cannot do that. There is no valid reference frame in relativity where the photon is sitting still, where its speed is zero. If you try to force the equations into a frame where light is at rest, the math demands an infinite gamma factor and breaks down. So straight away, light is different. It does not admit a rest frame the way massive objects do. To see what that means for time, go back to the space-time picture. Between any two events, say event A and event B, you can define a kind of space-time distance that mixes both the time difference and the space difference. You take the time difference between the events, multiply it by light speed to turn it into a distance unit, and then you compare that with how far apart the events are in space. You don't just add these like normal Pythagoras, you take the square of the time part times light speed squared, then subtract the square of the space part. That combination is what we call the space-time interval. This interval has three possible types. If the time part is big enough compared to the space part, the interval comes out positive. Those are time-like separations, the kind that massive objects like you can travel along. If the space part is too big compared to the time part, the interval comes out negative. Those are space-like separations, which would require faster than light travel and are therefore forbidden for real particles. And then there's the boundary case, where the time part and the space part exactly balance. In that case, the interval is exactly 0. Those are the null or light-like separations, and those are precisely the paths that light follows. Now link this to proper time. Proper time is the time your own clock measures as it travels along its world line, its path in spacetime. In the math, proper time between two events is directly proportional to the square root of that spacetime interval for time-like paths. If the interval is positive, you can take its square root, and that gives you a non-zero amount of proper time. That's what happens for any massive object moving slower than light. Between leaving Earth and arriving at Mars, for example, your world line has a positive interval and you age by some number of seconds, minutes, days, whatever. But for light-like paths, where that space-time interval is exactly 0, the square root is also 0. That means the proper time along a photon's path between emission and absorption is 0. Not small, not very slow, literally 0. In the formal language of relativity, there is no proper time evolution along a light-like world line. Between a photon being emitted in a galaxy 10 billion light-years away and being absorbed in your telescope, 10 billion years may pass in the coordinate time of your frame, but the proper time along the photon's own path is exactly 0. This is where the statement "time stops at light speed" is exactly true. But only in this very specific sense. For photons traveling along null paths, the proper time between any two events on that path is 0. Time does not march forward along that trajectory. For you, with mass, your time can be stretched and twisted relative to other observers as you approach that boundary, but it never fully stops. You can get arbitrarily close to living on the edge of light-like behavior, but you can never jump over and see the universe the way light does, because there is no valid way to define that viewpoint. The next step is to zoom out from individual particles and look at the whole space-time map, the world lines of objects, and the light cones that define what can influence what. Once you see how light speed shapes that geometry, you'll see why this 0 proper time at light speed is not a side detail. It's the skeleton of cause and effect itself. Here's the deeper question hiding under everything so far. If light owns the 0 time paths, how does that actually lock down what's possible and what's impossible in the whole universe, not just for one particle? Think of every object, including you, as drawing a track through space-time. At each moment, you are at some place and some time. That's one event. A second later, you're at another event. Link all those events together and you get a curve. That's your world line. If we draw a simple diagram with time going up and one space direction going sideways, a person sitting still in one spot has a world line that's almost vertical. Time passes, but their position doesn't change. A moving object has a world line that tilts away from vertical, because as time increases, position changes. The faster the object moves through space, the more tilted its world line is in that diagram. But as long as it moves slower than light, the line never tilts so far that it becomes almost horizontal. Now pick one event on that diagram, say you snapping your fingers in your room right now. From that event, you can ask what places and times can be influenced by this snap if you send out signals at light speed or slower in all directions. If you draw all possible light rays leaving that event, going up and out at the maximum slope allowed by light speed in every spatial direction, you get a double cone shape in the full space-time picture. In the simple time-space sketch, it looks like two lines at 45 degrees, one going up to the right, one up to the left. All future light signals lie on the surface of the top cone. All past light signals that could have reached you right now lie on the surface of the bottom cone. Everything inside that future cone above your event is reachable by you if you move slower than light and send signals slower than or equal to light speed. Everything inside the past cone is what could have affected you. Events outside the cone are different. They are so far away in space or so close in time that even light can't connect your snap to them. To influence those, you'd have to send a signal faster than light. To be influenced by those, something would have had to travel to you faster than light. That's why the light cone is really a causality map. Inside the cone, cause and effect can be linked by signals moving at or below light speed. Outside, they cannot. The key rule of relativity is simple and strict. Physical world lines, the paths that real objects and particles take, must stay inside or exactly on their light cone, never outside. If you stay inside, your speed is less than light speed. If you are on the cone, your speed is exactly light speed. That's where photons live. If you try to draw a world line that goes outside that cone, you're drawing a path that would require faster than light motion. Immediately, causality breaks, because then you can find observers for whom the effect comes before the cause. That's why we say faster than light travel is not just about going quick, it really would scramble the order of events. Now connect this to proper time. Take two events on your own world line, say your birth and your death. There are many possible paths through spacetime connecting them, depending on how you move, whether you stay on Earth, travel in a spaceship, orbit a black hole, and so on. Each of those paths is time-like, inside the light cone, and each one accumulates some amount of proper time. That's how much you age along that route. One path might give you 80 years of proper time. Another, if you spend decades at high speed, might only give you 30 years, while the rest of the universe ages much more. Different time-like paths between the same two end events can yield different proper times. For time-like paths, the space-time interval between those events is positive, and the square root of that interval converted by light speed gives you a positive proper time. For light-like paths, the ones on the cone, the interval is 0 and proper time is 0. That's why light does not age along its path. For space-like paths, the ones outside the cone that are not physically allowed, the interval comes out with the opposite sign. And if you try to treat that like proper time, you'd get an imaginary value, not something you can interpret as real time experienced by an object. That's nature's way of saying these paths are not for real matter or real observers. So when you say time stops at light speed, this space-time picture lets you restate that in a sharper way. The set of all possible future events that you can influence is bounded by your light cone. Inside that cone, along time-like paths, proper time always increases. Clocks tick, aging happens. On the cone itself, along light-like paths, the space-time interval is 0 and proper time vanishes. That's boundary, the cone, is the edge of allowed causal influence for you, and it's exactly where light lives. Light speed is not just a speed limit number, it's the slope of the boundary between causally connected and causally disconnected, between time flows and proper time is 0. You're basically telling yourself the reason you cannot go faster than light is not only about energy cost, it's about not being allowed to draw a world line outside your light cone. If you could step outside, you could arrive at an event before you left in some frame. You could send information into your own past. You could break the entire chain of cause and effect. The universe prevents that by locking your world line to time-like or at most light-like paths. On those allowed paths, proper time is always non-negative. It's positive for massive objects, 0 for light, never negative, never imaginary. Seen this way, the phrase "time stops at light speed" is not just a catchy line. It becomes proper time vanishes right on the geometric boundary of causality. Everything we've talked about, from light clocks to GPS to muons in the atmosphere, is just different ways of sampling that geometry. The closer your world line leans towards the light cone, the less proper time you accumulate compared to the outside universe. Sit exactly on the cone, you're light, and you accumulate none. Try to go outside the cone, and you've left the space of physically possible motion. So far, we've talked about abstract observers and particles. But what happens if we plug a human story into this geometry and actually compare two people's world lines that split and then rejoin? Who comes back older? Who comes back younger? And how close can we push that gap towards the time almost stops regime? How far can you actually push this slow time trick for a real person? How big can the gap get between your life and everyone else's? Set up the classic scenario. You and your twin start together on Earth. One twin stays home. You get on a ship that can cruise at a constant speed of 0.8 times light speed. That's 80% of about 300 million meters per second. So roughly 240 million meters per second, roughly 540 million miles per hour. You head out into space, then after some time, you turn around and come back at the same speed. From Earth's point of view, suppose the whole trip going out and coming back takes 10 years of Earth time. The clocks on Earth tick 10 full years between your departure and your return. But at 0.8 times light speed, we already know the gamma factor, the time dilation factor, is about 1.67. That means your moving clock, your body, your onboard watch, all run slower by that factor compared to Earth's clocks. So if Earth sees 10 years pass, you only rack up 10 divided by 1.67, which is about 6 years of proper time. When you step off the ship, your twin on Earth has aged 10 years, you've aged about 6. Nothing magical happened. From your point of view on the ship, your heart rate felt normal, your watch ticked normally, your aging felt normal. You lived through 6 years. From your twin's point of view on Earth, their life also felt normal. They lived through 10 years. It's only when you reunite and put your clocks and your faces side by side that the difference shows up. The paths your world lines took through space-time had different proper times between the start together event and the meet again event. Now scale this up. Instead of 0.8 times light speed, you travel at 0.99 times light speed. Gamma jumps to about 7.1. If Earth measures 10 years of your trip again, you only age about 10 divided by 7.1, a bit less than 1.4 years. Your twin goes from, say, 30 to 40, you go from 30 to a bit over 31. Push the speed further, 0.999 times light speed, gamma's about 22. Keep the 10 Earth years, you age only about 5.5 months. You can see how this escalates. The closer your speed gets to light speed, the more the age gap explodes. From your proper time point of view, the trip is always short, but in the external frame, huge chunks of history can pass. You might say, okay, but that's just thought experiments. Has anything like this actually been measured for real clocks? Yes, but on much smaller scales, because we can't accelerate people to 0.8 times light speed. However, the same effect has been seen many times with atomic clocks. Fly a very precise clock on an airplane around the world, keep another identical clock on the ground. When you bring them back together and compare them, the one that flew shows a tiny difference, often nanoseconds, billionths of a second, compared to the one that stayed. Put clocks on satellites in orbit, like we do with GPS, and you see microsecond level offsets, millionths of a second, that match the predictions from special and general relativity combined. For human biology, nanoseconds and microseconds don't matter. You won't feel younger after a commercial flight. But the principle is exactly the same as in the twin paradox story, just with tiny gamma factors because the speeds are tiny compared to light. As technology pushes speeds higher, the same math would give bigger and bigger differences. The twin paradox isn't a paradox at all. It's just time dilation applied to two different world lines that meet twice. Now, push your imagination and your math to the edge. Suppose you could build a ship that accelerates long enough to reach some enormous gamma, like 100 or 1,000. At gamma 100, for every 100 years that pass on Earth, you might only experience about 1 year on the ship. At gamma 1,000, for every 1,000 years on Earth, you get 1 year. In the limit where gamma goes to infinity, which corresponds to your speed approaching light speed, your own aging, your proper time between departure and return, tends towards 0, while the external universe can age by any amount. You could leave, wait what feels like a few days or minutes to you, and come back to a galaxy that's millions of years older. This is the time nearly stopped for the traveler scenario made precise. From Earth's perspective, your ship's clocks run extremely slow. From your perspective, your clocks are normal, but you see the external universe's clocks racing ahead. Stars spin, galaxies evolve, civilizations rise and fall, all in what feels like a very short proper time for you. The gap between your time and their time is controlled entirely by gamma. But notice something crucial here. In every version of the story, your proper time is always moving forward. Your heart beats in one direction. You go from younger to older. Your clock hands move clockwise, never backward. There is no frame in which you see your own proper time reverse. Time dilation is not time reversal. Even in the crazy limit where gamma is extremely large, your proper time is still a positive number between departure and arrival. Maybe it's minutes instead of years, but it's never negative, it's never zero for a finite journey, and it never loops back. That's why this doesn't break causality. You and your twin agree on the order of key events. You left, you traveled, you returned. They might say a lot happened while you were gone. You might say, I experienced very little while a lot happened there, but the sequence is consistent. No messages arrived before they were sent. No one experienced yesterday after today. Time dilation changes how much time passes along different paths, not the direction in which it flows. So once again, you see light speed showing up as a limit in two ways at once. As you push closer to it, your required energy, your gamma, and your time dilation all head toward infinity. Your proper time between fixed external events heads toward zero. That's the same structure we saw with photons in zero proper time, just approached from the massive side. You can move along time-like paths that lean very close to the light cone and get very small proper times. But the only way to actually hit zero proper time for a finite separation is to write a light-like path, and that's reserved for massless particles. We've now brought speed, energy, and clocks together, and you've seen how near-light travel lets you almost freeze your own time relative to the universe. But motion isn't the only way to twist time. Gravity does it too. The next step is to see how curvature of space-time itself can slow clocks, and how in extreme cases, that time slows down effect starts to look very similar to what happens as you approach light speed. So far, speed has been doing all the work in bending time, but what happens when you don't move at all and time still slows down just because of where you are? In Einstein's general relativity, gravity isn't a force pulling things down in the old sense, it's curvature of space-time itself. Mass and energy bend space-time, and objects, including light, follow the curves. One big consequence is this. Clocks deeper in a gravitational well tick slower than clocks higher up. Even if both clocks are just sitting still, not moving through space, their rates are different. Take Earth. A clock at sea level is slightly deeper in Earth's gravity than a clock on a mountaintop that's a few kilometers higher, a few thousand feet. According to general relativity, the clock at sea level runs a tiny bit slower. The difference is ridiculously small, nanoseconds per day, billionths of a second per day, for height differences on the order of tens or hundreds of meters. But with modern atomic clocks, we can measure that. Move a clock up a building, its tick rate changes. You don't feel it, but physics does not care about your feelings. The numbers shift. To make sense of this, think in terms of gravitational potential, basically how deep you are in the gravity well. Near Earth, you can approximate the effect like this in words. The rate of a clock is multiplied by 1 plus the gravitational potential divided by light speed squared. The potential is a negative number that becomes more negative the deeper you are. So deeper down, that correction factor is a bit smaller, and time runs a bit slower. Higher up, the potential is less negative, the factor is larger, and time runs faster. Again, the important thing is that the effect is small but real. Between the ground floor and the top of a tall building, over one day, you might get a difference of a few nanoseconds. Over a year, microseconds. Over a lifetime, you could, in principle, add it up and say, people living on mountaintops age a tiny bit faster than people at sea level, purely due to gravity. The numbers are tiny, but unlike sci-fi, we can literally measure them with lab equipment. Now connect that to the earlier GPS story. There, we saw two contributions messing with satellite clocks. One comes from motion, the special relativistic effect. The satellites move at about 3.9 kilometers per second, about 8,700 miles per hour, so their moving clocks tend to run slow by roughly 7 microseconds per day compared to Earth clocks. The second contribution comes from gravity. They're about 20,200 kilometers up, where Earth's gravity is weaker, so their clocks tend to run fast by about 45 microseconds per day compared to clocks on the surface. Add those together, and you get a net speedup of about 38 microseconds per day. We correct for that so your phone works. That example is important because it shows you both effects at once: motion-based time dilation from special relativity and gravity-based time dilation from general relativity. They're not two separate, unrelated weird things. They're two faces of the same underlying geometry, space-time being curved and objects following different paths through it. GPS is a low-intensity demonstration. At 3.9 kilometers per second and weak gravity, we already care about tens of microseconds per day. The question is, what happens if you ramp up the gravity the same way we ramped up the speed? Move away from Earth and think about really compact objects. Take a neutron star, a collapsed stellar core with a mass greater than the Sun, squeezed into a sphere about 10 to 20 kilometers across, roughly 6 to 12 miles. The gravitational field near its surface is extreme. If you could hover just above it, a clock on your spaceship would tick much slower compared to a distant clock far from the neutron star's gravity. Minutes for you could line up with hours far away, depending on how close you are. Sit even closer to the surface and the difference grows. You haven't changed your speed much, you're just sitting in a very curved space-time, and time itself is being stretched. Now push it further, near a black hole. For a non-rotating black hole, there's a critical radius called the Schwarzschild Radius, basically the event horizon. For a black hole with 10 times the mass of the Sun, that radius is around 30 kilometers, about 19 miles. If you hover just outside that radius, holding station with rockets, the gravitational time dilation becomes enormous. From your point of view, your clock ticks normally, your heart beats, your thoughts flow. From the point of view of a distant observer far away, your clock is crawling. You might experience only a few minutes while the remote universe ages by hours, days, or longer, depending on how close you sit. If you move him in closer, asymptotically approaching the event horizon without crossing it, the time dilation factor relative to the distant universe can grow without bound. In the extreme limit, just like with speed, you can imagine your proper time between two distant universe events becoming very small, while the outside world evolves dramatically. This is the gravitational version of riding the edge of stopped time. You don't have to move fast, you just have to sit deep in a gravity well that's strong enough. So now you have two knobs that can slow time. One knob is velocity, your speed relative to some frame, which cranks up the gamma factor from special relativity. The other knob is gravitational potential, how deep you sit in a gravity well, which bends space-time and changes clock rates according to general relativity. In real situations, both knobs are often turned a little bit at the same time. Satellites in orbit feel both effects at once. A person falling into a black hole experiences both huge gravity and high speeds as they drop. The unified picture is this. Spacetime is a four-dimensional geometric object, and light speed sets the structure of that geometry. Mass and energy curb it. When you move fast through space or sit deep in a gravity well, or both, your path through spacetime changes in a way that reduces how much proper time you accumulate compared to someone far away and slow. Time slows for you relative to that distant observer, but your own clock always runs normally in your frame. And just like with speed, there is an extreme gravitational limit that starts to look like time stopping. At an event horizon, light can be forced to hover, stuck riding along the horizon itself. The proper time along those paths is zero, just like any light-like path. Clocks hovering just outside that horizon can experience very little proper time while the outside universe rushes by. It's the same theme again. Whether you try to smash into light speed with rockets or drop toward a black hole's horizon, the geometry of space-time is what decides how much time you get to experience. So now the natural next step is obvious. If gravity can slow time this much, what happens at the place where even light can't escape, where the escape speed itself equals light speed and time dilation from gravity and the light speed limit collide head-on? There is a place in the universe where the usual rule, if you go fast enough you can get away, just stops working, even for light itself. Start with a simpler classical idea of escape velocity. Take a planet or a star with some mass m and think about launching a rocket from a distance r from its center. Gravity is pulling you back. If you want your rocket to get away forever, not fall back, you need a minimum launch speed, the escape velocity. In basic gravity physics, that speed is given by a simple relationship. Escape velocity equals the square root of 2 times the gravitational constant times the mass divided by the radius you're starting from. You don't have to memorize the exact expression. The key is this. For a fixed mass, if you get closer in, r gets smaller, and the escape speed gets larger. Move far away, escape speed drops. Move inward, escape speed rises. For Earth, that minimum speed is about 11.2 kilometers per second, around 25,000 miles per hour. For the Sun's surface, it's a few hundred kilometers per second. Now push the mass up and the radius down together. As you squeeze mass into a smaller radius, the escape speed from that radius climbs. If you compress enough mass into a small enough sphere, there's a radius where the escape velocity becomes equal to light speed, about 300,000 kilometers per second, about 186,000 miles per second. That radius has a name in general relativity, the Schwarzschild Radius. The Schwarzschild radius is given by 2 times the gravitational constant times the mass divided by the square of light speed. The structure is similar to the escape velocity expression, but now you're solving the equation escape velocity equals light speed for the radius. For a black hole with 10 times the mass of the Sun, that critical radius is about 30 kilometers, roughly 19 miles. If you took 10 suns worth of mass and somehow compressed it into a sphere about the size of a city, the surface of that sphere would sit at this radius. At that location, the escape velocity is exactly light speed. Inside that radius, even light, which always moves at light speed locally, cannot climb out to infinity. Once you cross that radius going inward, you do not come back out. That radius defines the event horizon of a non-rotating black hole. So what does time do near that horizon? From the point of view of a distant observer far from the black hole's gravity, something strange happens. Imagine you drop a clock toward the black hole and watch it through a telescope. At first, the ticks seem normal. As the clock gets closer to the event horizon, the ticks you see get slower and slower. The light signals carrying those ticks get redshifted and spaced out. In the distant observer's coordinate time, the infalling clock appears to take longer and longer to approach the horizon, and you never actually see a cross. Its last few ticks take an absurd amount of your time to arrive. In that external frame, it looks like the clock is freezing on the horizon, its time stretching out. But from the clock's own point of view, that is not what happens. The clock is in free fall. Locally, it feels weightless, like an astronaut in orbit, ignoring tidal forces for the moment. Its own proper time runs normally. If you ride along with it, your heart beats, your watch ticks, you count seconds in the usual way. You cross the event horizon in a finite amount of your proper time. Depending on the size of the black hole, it might be seconds, minutes, or hours, but it is not infinite. Once inside, you keep falling toward the center, toward the singularity, again in a finite proper time. The freezing on the horizon is only true from the view of the distant observer looking back out along the warped spacetime. This difference is easier to picture if you go back to light cones. Remember, at each event in spacetime, you can draw a cone that marks out all possible light paths going forward in time. Inside the cone, slower than light paths live. On the cone, light paths live. Outside, forbidden faster than light paths would live, but they don't occur for real objects. In flat spacetime far from gravity, those cones are nicely upright. The up direction is your future, and part of up and out points away from whatever mass there is. Near a black hole, spacetime is curved so strongly that these cones tilt. As you get closer to the horizon, the future direction inside each light cone leans more toward the black hole. The options for where you can go next while staying inside your light cone narrow. Right at the event horizon, the cone is tipped so far that the outward light-like direction, the path that just barely avoids falling in, lies exactly along the horizon itself. Light emitted outward at that precise radius never reaches a larger radius. It just crawls along the horizon. Inside the horizon, the tilt is even more extreme. Every possible future-directed path, even at light speed, points deeper in, toward the singularity. There is no direction inside the cone that leads back out. Combine that with what you already know about proper time. Light-like paths have zero proper time. At the horizon, light that tries to go outward is forced to travel along a surface where, in the spacetime geometry, the spacetime interval is null. It's another situation where light is stuck on a boundary, riding a path with no accumulated proper time. A clock hovering extremely close to the horizon, held there by some hypothetical engine, would have its time slow down tremendously relative to the outside universe. In the limit where you hover arbitrarily close to the horizon, the amount of outside time that passes for each tick of your clock tends toward infinity. That is the gravitational version of time stops, right at the border where light itself is barely able to hang on. So black holes tie together the two main themes. The escape velocity hitting light speed gives you a radius where no signal, not even at light speed, can climb out to infinity. The space-time curvature there tilts light cones until future inside them points inwards, locking in the one-way nature of the horizon. And the proper time behavior shows that for light at that boundary, time does not advance, while for massive objects hovering just outside, time runs arbitrarily slow compared to distant observers as you push closer and closer to that radius. You can see the analogy clearly now. For motion, as you approach light speed relative to some frame, your gamma factor grows without bound, your kinetic energy explodes, and your time dilation relative to that frame goes to infinity. For gravity, as you approach an event horizon and try to hold station just above it, the gravitational time dilation relative to faraway observers also grows without bound, and light emitted outward becomes more and more redshifted and delayed. In both cases, the stopped time limit appears as a boundary you can't actually cross while still sharing a standard notion of time with distant observers. So this naturally raises a question that pulls attention even tighter. If time can be slowed down so brutally by speed and gravity, is there any way at all to jump outside the structure, to cheat the light speed limit by going around space-time instead of through it, or by using exotic tricks like faster-than-light particles, warp drives, or shortcuts in the geometry itself? If time slows down more and more as you get close to light speed, the obvious next question is there any loophole at all? Any way to beat that limit instead of just crawling closer forever? First idea people jump to is faster-than-light particles themselves, things that would never go slower than light. These are what theorists call tachyons. By definition, a tachyon would always move faster than light. It could speed up and slow down within that superluminal range, but it could never cross down through light speed to match you. On paper, you can plug faster than light into the space-time formulas. When you do that, the space-time interval between its events comes out as space-like, not time-like. And if you try to treat that interval as proper time like you do for normal particles, you get an imaginary number, not a real amount of time. That's a sign that the mathematics is telling you this doesn't behave like normal matter at all. Even worse, if tachyons could interact with normal matter in standard ways, you could set up situations where signals go backwards in time. In some frame, you send a message and receive the reply before you sent it. That crushes causality. So right now, tachyons are more like a warning label in the equations than a real candidate for new physics, and we have never seen any experimental hint of them. So if actual faster-than-light particles are this toxic for causality, the next move is to ask, can you keep local speeds below light speed, but cheat by modifying space-time itself? That's where ideas like warp drives and wormholes come in. The basic concept of a warp drive, like the Alcubierre drive, is that you don't move faster than light through space. Instead, you make space in front of your ship contract and space behind your ship expand. From your local point of view, you are just sitting inside a bubble not breaking the light speed rule. But relative to distant points, the bubble itself moves in a way that makes it look like you went from A to B faster than any light beam traveling in normal, unwarped space could have. Traversable wormholes are similar in spirit. Instead of moving faster than light from A to B, you connect A and B with a shortcut tunnel in spacetime, like a bridge. Locally, you could walk through that tunnel at a normal, slow speed, but because the two mouths of the wormhole are very far apart in normal space, it looks like you have covered that distance too quickly when viewed from outside. In both cases, you're not breaking the local speed limit. You're bending or connecting spacetime so that the long path shrinks. The catch is harsh. When you solve the Einstein field equations and ask, what kind of matter or energy do I need to hold open a stable wormhole or create a warp bubble, the answer is you need exotic matter. Specifically, you need regions with effectively negative energy density relative to normal vacuum. That's not just unusual fuel, it's something we do not know how to produce in bulk, and that may not be possible in any macroscopic stable form. Quantum field theory lets you have tiny, brief negative energy fluctuations in very constrained ways, but nothing like the sustained large negative energy required for a galactic scale highway. So warp drives and wormholes are interesting solutions on paper, but they sit in a category of speculative, probably impossible with real physics as we currently understand it. There's another common source of confusion, and this one actually happens in labs and reactors. People say, we already see faster than light particles. What about that blue glow in nuclear reactors? That's Cherenkov radiation. Here's what's going on. In a medium like water or glass, light does not travel at its vacuum speed. Interactions with the material slow it down, so its effective speed might be something like 0.75 times light speed in vacuum. But particles like electrons or other charged particles can move through that medium faster than this reduced local light speed, while still staying below the true vacuum light speed. When they do, they create a shock wave in the electromagnetic field, which shows up as a blue glow, somewhat like a sonic boom but for light. The key point, they are only faster than light in that material, not faster than light in vacuum. The fundamental limit, the vacuum speed of light, is not touched. So theory gives you dangerous toys like tachyons and speculative geometries like wormholes and warp bubbles, and real phenomena like Cherenkov radiation that look superficially like faster than light motion but aren't. What does experiment say when you actually go hunting for any breakdown in the nothing outruns C rule? Physicists have been testing this for decades in very direct ways. They look for violations of Lorentz invariance, which is the symmetry underlying special relativity. If there were preferred directions in space or tiny differences in light speed for different energies or polarizations, we might see them in gamma rays from distant explosions, in high-energy cosmic rays, or in precision lab experiments. So far, every robust test shows that the speed of light and the rules of relativity hold to extremely high precision. There was even a famous claimed anomaly with neutrinos in the Opera experiment years ago. For a short time, their data seemed to show neutrinos arriving slightly earlier than light would, which if true would have been a bombshell. But after intense checking, the anomaly was traced to a hardware issue, basically a bad connection in the timing system. Once that was fixed, the faster-than-light signal disappeared. Other experiments measuring neutrino speeds have found them to be just under light speed, exactly where they should be for particles with a tiny but non-zero mass. Taken together, the experimental picture is brutally simple. Wherever we can test it, the vacuum speed of light shows up as a hard ceiling for signals and particles with mass. Things can get arbitrarily close from below, but nothing real crosses it. So why is C so stubborn? Why does it show up everywhere? Because it's not just a speed in one theory, it's a core constant wired into a lot of different pieces of physics. It sits inside Maxwell's equations for electromagnetism, where it's the speed of electromagnetic waves in vacuum. It defines the conversion factor between time components and the geometry of special and general relativity. It appears in the relation between energy and momentum in quantum field theory. It's the slope of the light cones that define what can influence what. If you let anything with mass casually exceed C, you don't just tweak one detail, you smash the coherence of that entire structure. And that's the real issue. If superluminal motion were allowed in an ordinary way, you could engineer situations where signals loop back in time in some frame, where A sends a message to B and B replies in a way that, from another observer's view, arrives before A sent the first message. That's causality breaking down. Every line of solid evidence we have says the universe does not permit that. It enforces C as a universal limit so that the ordering of cause and effect can be consistent for all observers who follow the real rules. So the answer, as far as we can tell today, is no. You don't get to cheat light speed with normal matter, normal signals, and normal spacetime. You can only write closer and closer to that boundary, and play games with how much proper time you experience compared to the outside universe. Which brings us back to the original question in a sharper form. If you can only ever approach C and never reach it, what exactly does time stops at light speed mean for you? And what does it truly mean for light itself? So does time actually stop at light speed, or is that just a dramatic line people throw around when the real story is way more specific? Here's the clean version. Along any path that light can take in spacetime, the proper time between emission and absorption is exactly 0. Proper time is the time measured by a clock that rides along that world line. For a photon, if you try to attach a clock to that world line and ask how much time it experiences between leaving a distant galaxy and hitting your eye, the answer from the math is none at all. The space-time interval along that path is what we call light-like, or null, and proper time is directly tied to that interval. For light, the interval is 0, so the proper time is 0. In that narrow technical sense, time doesn't pass for light. That's the one thing the phrase "time stops at light speed" gets exactly right. But that statement does not extend to you or to any object with mass. You can only move along time-like paths, where proper time is always positive. You can lean your world line closer and closer to the light-like boundary, but you never become light. For you, what you can do is decouple your own clock from the outside universe's clock by going very fast relative to some frame. The factor that measures that decoupling is the same gamma we've been using all along. At low speeds, gamma is almost 1, so your time and the universe's time match pretty closely. At high speeds, gamma grows, and the mismatch grows with it. If you somehow reach a gamma of 1000, that's a speed so close to light speed that the difference in meters per second is tiny, but the relativistic effects are huge. 1 hour on your ship's clock would line up with about 1,000 hours for someone on Earth, a bit more than 41 days. You experience an hour of real life, real thoughts, real aging. When you check in with Earth, they've lived through more than a month and a half. Push gamma to 10,000, and that 1 hour for you lines up with over a year for Earth. Keep cranking gamma and the gap explodes. You are not freezing your time, you are compressing your experience time relative to the outside world. Now link that back to the limits. As your speed relative to some external frame gets closer to light speed, gamma shoots upward. In the mathematical limit where your speed approaches light speed, gamma goes to infinity. That same factor, gamma, controls your kinetic energy, so your required energy also goes to infinity. It controls time dilation, so the ratio between their time and your time also goes to infinity. For a fixed pair of external events, like you leave Earth and you reappear somewhere else, the proper time you personally experience between those events shrinks towards 0 as gamma grows. Put that list in words. Speed towards light speed, gamma blows up, energy cost blows up, proper time along your path shrinks to 0. That triple lock is what keeps you from ever actually reaching the state where your proper time is truly 0. Light owns that limit. Massive objects can only approach it asymptotically at an infinite energy cost. If you could somehow ride with a gamma that is huge but finite, the universe would look very strange in your forward direction. Light coming from ahead would be highly blue-shifted, squashed into higher frequencies. The sky in front of you would appear compressed into a bright, narrow cone. Objects and distances in front of you would look contracted along the direction of motion. Meanwhile, clocks out in the rest of the universe would be ticking like crazy compared to yours. Events that, in some external frame, are separated by years or centuries could sweep by while your onboard clock counts minutes or hours. It's not that time stops everywhere when you go fast. It's the opposite. The outside cosmos is busy, writing a lot of history, while your own clock barely advances. That's the key mental shift. Time stops at light speed. It's not about the universe freezing when you go fast. It's about your proper time becoming almost disconnected from the rest of the universe's story as you approach the light-like boundary. Your own timeline shrinks while the external timeline stretches. At the exact boundary for a photon, that shrinkage hits 0 proper time. For you, with mass, you can only ever get close enough that the difference becomes huge, never infinite. The reason this feels so alien is that nothing in everyday life trains you to think this way. Your typical speeds are a joke compared to light speed. Cars at 100 kilometers per hour, about 60 miles per hour. Airplanes at around 900 kilometers per hour, about 560 miles per hour. Even rockets at a few kilometers per second. These give gamma values so close to 1 that you can ignore the difference. So your brain defaults to a Newton-style picture, where time is just a uniform background, the same for everyone, and only space changes. That approximation works so well in normal conditions that it becomes your common sense. But look at the evidence you've just walked through. Muons created 15 kilometers above you that by simple non-relativistic logic should die after 660 meters are hitting detectors at sea level because their clocks are time dilated by factors of 10, 15 or more. Particle beams and accelerators survive hundreds or thousands of times longer than their rest lifetimes because gamma is huge. GPS satellites must have their clocks pre-tuned to correct for tens of microseconds per day of relativistic time dilation, or your phone's location would drift by kilometers. Clocks on airplanes and mountaintops tick at measurably different rates than clocks at sea level because of both motion and gravity. And black holes with escape velocity equal to light speed at the Schwarzschild Radius create regions where clocks near the horizon run arbitrarily slow compared to clocks far away, and where light itself can get trapped at that boundary. All of those systems, cosmic rays, accelerators, satellites, precise clocks, and black holes and X-ray binaries, are screaming the same thing at you. Time is not a single rigid flow. It is a quantity that can stretch and squeeze depending on velocity and gravitational potential, all within a space-time geometry built around the speed of light. Along a light-like path, that stretch is driven all the way down to zero proper time. Along time-like paths, you can push your proper time arbitrarily close to zero between two external events, but only by paying an infinite energy price in the limit. That's why time stops at light speed is true for light, and only as a limit, never as a reachable travel mode for you. You don't get to ride a photon and watch the universe flash by in zero time, but understanding why that's forbidden and how close you can get is what really tells you how the universe is wired. It's not built around your everyday sense of one shared time. It's built around C, the speed of light in vacuum, as the skeleton of space-time and causality, with your experience of time as one flexible local slice through that structure. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. If you enjoyed the video, consider subscribing to the channel and like the video.